Okay, now we can get started with the actual material in Chapter 4. So again, Chapter 4 is all about reactions and aqueous solutions. So in Chapter 3, we learned about several different types of reactions. We learned about combination reactions, decomposition reactions, and combustion reactions. Now in Chapter 4, all of the reactions that we're going to learn about have something in common, or at least most of them have something in common. And that is they all occur in water. And that's what we mean by when we say aqueous solutions. So for example, if you see something like this, NaCl, and it has a parentheses AQ behind it, what that means is that sodium chloride has been dissolved in water. So you have a water solution that has sodium chloride dissolved in it. And that's what this AQ, aqueous, is standing for. Okay, so the first type of reaction we're going to learn about is something called a metathesis or exchange reaction. Now, this is a reaction where the cations and the anions exchange partners. So, for example, if we have cations A and B, and they are paired with anions X and Y, so these are our two reactants. The products that they form, the cations stay in the same place. So we're going to have A and B. But on the product side, what's going to be different is the anion that they're paired with. So on the reactant side, X was paired with A. So that means on the product side, we want X to be paired with B. Now, the anion Y on the reactant side was paired with B, so on the product side, we are going to want Y paired with A. So this is called a metathesis or exchange reaction. It's two different words for the same type of reaction. So the cations and anions exchange partners. So there are different types of exchange reactions, and we're going to learn about one of those types now, called a precipitation reaction. Talk about precipitation reactions. Now, a precipitation reaction is a reaction that occurs when two soluble ionic compounds, meaning two compounds that can dissolve in water, are mixed together. They exchange partners, like how we saw in the exchange reactions, but one of the products is insoluble, meaning it cannot dissolve in water. And since it can't dissolve in water, what it does is it forms a solid. Now, the more specific term for the word solid would be a precipitate. So in a precipitation reaction, a precipitate is formed. And what that basically means is just that in a precipitation reaction, when chemicals in a solution react, one of them forms a solid. So now, they'll basically always have the form of some kind of compound that's aqueous, is going to be combined with some other kind of compound that's aqueous, and they're going to yield one product that's insoluble, meaning it forms a solid. It cannot dissolve in water, so it forms a solid, and this solid is also called a precipitate. And then the other product is going to be aqueous. It's going to stay dissolved in water. So what's in these blanks here will be different types of compounds, and the type is not really as important. You just have to be able to identify that when you have two soluble compounds, so two things that can be dissolved in water, and that's why they're aqueous, and they mix together, they exchange partners, and one thing forms a solid because one of the products will be insoluble, so one thing forms a precipitate, and the other thing stays dissolved in water. It's still aqueous. So in a precipitation reaction, one of the products has to form a solid. So we know that. We know there has to be a solid. But the next question then becomes, well, how do we tell if one of the products forms a solid or not? And we tell that information, we can find that information out by looking at this chart. Now this chart is from your textbook, and it's called the solubility table or guideline, or you'll see different words for it. Now it's important that you understand how to use this chart. So the chart gives a list of anions right here and right here. And again, I know these are anions because they are negatively charged. And it breaks the anions up into two categories. It breaks them up into soluble anions and insoluble anions, meaning that the anions listed right here in the soluble part do not form solids. They generally dissolve in water when they're formed with different cations. So the phase of these will be aqueous. Now there's one really big exception here, or important thing to note, are these important exceptions right here. Now, if these anions right here are paired with any of these cations, the compound then becomes insoluble, meaning it does not dissolve in water, and as a result, forms a solid. Okay? So if you look at these anions right here, we need to look at the cation that they're attached to. If the cation is any of these exceptions, then the compound is insoluble and forms a solid. But if the cation is not any of these exceptions, then the compound is soluble. It dissolves in water, meaning the phase on it stays aqueous. Okay, now the bottom part of the chart is pretty much the exact opposite. These four anions right here are usually insoluble, meaning that when they're paired with most cations, the phase on them will be solid. So they form precipitates. Unless they are paired with any of these cations. If they're paired with any of these cations, then they become soluble, meaning that they dissolve in water and their phase will be aqueous. Okay, so when we write our products out for precipitation reactions, we need to come to this chart and we need to look at our anions on our products. And then we need to take a look at the cations that those anions are attached to. And we need to see, are the cations any of these exceptions? If they are, then the phase is according, you label it accordingly. If they're not, then the phase is just whatever part of the table it's in, either soluble or insoluble. So let's take a look at, we'll write a precipitation reaction together so that you can really get a feel for how to use this table. Okay, let's say we have silver and nitrate in aqueous solution, and that is reacting with potassium chloride in an aqueous solution. And we want to know if when these two compounds come together, if they form a precipitation reaction. Now, there are multiple steps in doing these precipitation reaction questions. Just to kind of give you a big picture overview of how we go through them, the first thing we do is we have to write the products correctly keeping in mind the charges of the ions. Okay, so that'll be step 1. Step 2 will be to use this solubility table and see if either one of our products forms a precipitate, if it forms a solid. Then finally, we need to make sure the equation is balanced. Okay, so there are 3 parts to answering precipitation reaction questions. Okay, so let's get started. So, if you remember, when we did the example of the exchange reaction, we said that in an exchange reaction, the cations stay in the same spot. So you have to be able to identify cations versus anions. So in this equation, the cations are silver and potassium. Okay, so those are our cations. So the cations are going to stay in the same spot. So we have Ag and we'll have K. Now the anions are going to change places. So the anions, let me get the highlighter here. The anions are nitrate, which is one of your polyatomic ions, and chlorine. Okay? So on the reactant side, nitrate is paired with silver. So that means we want nitrate to be paired with potassium on the product side. So I'm going to put nitrate right here. Okay. Now our other anion is chlorine, which is paired with potassium on the reactant side. So we're going to want chlorine paired with silver on the product side. Okay, now we need to make sure that we have these compounds written correctly, keeping in mind the ionic charges. So we need to go back to our reactants and figure out the charge that each of these ions form to make sure that we have the products written correctly. So if we look at this reactant first, potassium chloride, we can go up to a periodic table, and I'm going to write potassium chloride right here. Okay, so we need to figure out the charges of these ions. We can do that by looking at the periodic table. So where's potassium? Potassium's right here. It's in the first column, and those elements in that column form +1 cations. Chlorine on the periodic table is in this column right here, and elements in this column right here form -1 cations. If we have +1 and -1, the charges cancel out, and we're left with an overall, a compound with a net charge of 0. So that's perfect. So that's exactly what we want. So if we go back down here to our reaction, we're going to write that in. We're going to write potassium as a plus charge and chlorine as a -1 charge. Okay, now let's look at silver nitrate. Go back up. Let me erase this, and I'll write silver. Actually, this might be a little bit easier to see if I do this. Let's get rid of that. Okay, silver nitrate. What are the charges that each of these ions form? This one is a little bit more difficult because silver is right here. It's a transition metal, meaning that it doesn't have one specific charge. It could have different charges. And nitrate is a polyatomic ion, so it's not on the periodic table at all. So this is why it's so important to have the names and the charges of your polyatomic ions memorized, because that's the only way you can answer this question. So if you have your polyatomic ions memorized, you'll know that the charge of the ion for nitrate is a -1. So what does the charge of silver have to be for this thing to have a net charge of 0? Well, if nitrate is -1, that means silver has to be +1, and it will have now it has a net charge of 0. So we can go back to our reaction and write that information in. So we said silver was +1, nitrate was -1. Okay, so now we need to write those charges in on our products and make sure that they have an overall charge of 0. So silver we said was +1, chlorine is -1. Do those have a net charge of 0? They do. +1, -1 equals 0. Perfect. Potassium has a charge of +1. Nitrate, we figured out, has a charge of -1. Okay, so again, +1, -1. Do those charges cancel out to equal 0? They do. Okay, so we don't have to add any subscripts here to alter the amount of elements we have so that the net charges equal 0. So that step is done. We have our products written correctly. Now we need to take a look at the solubility table and figure out, do either of these products form a precipitate? So let's look at the anion nitrate first. So we have an anion nitrate, and here's nitrate, and it's generally soluble, unless, well, it doesn't have any exceptions, meaning it's always going to be soluble. So if something's soluble, it means it dissolves in water, and therefore the phase is aqueous. So I'm going to zoom in here, and I'll write AQ for aqueous. Okay, now let's look at our other product. Our other product, the anion, is chlorine. If we look on this list, we find chlorine. It's right here. It's usually soluble unless it's paired with any of these three things. Now, in our example, in our product, is chlorine paired with any of these three things? It is, right? Right here, silver. Silver is an exception. So normally chlorine is soluble, but because it's paired with silver, it makes it insoluble. And that means that this product right here forms a precipitate. So that is going to be a solid. Okay, so we have our reactants, we correctly wrote our products, and now we've identified which one forms a precipitate. The last step is to balance. Now, when you're balancing precipitation reactions, instead of writing silver, NO, K, and Cl, it will make your life so much easier if you keep the polyatomic ions together. So instead of breaking apart the nitrogen and the 3 oxygens, I'm going to keep it as nitrate. It will make balancing these types of equations so much easier. Okay, so if we look, we have 1 silver, 1 nitrate, 1 potassium, 1 chlorine, and on the product side we have 1 silver, 1 nitrate, 1 potassium, and 1 chlorine. Okay, so this equation is balanced. So then that means that this reaction right here is our final answer. This is the precipitation reaction. Okay? Let's try another one. So I wrote out some steps that can help you go through all the steps for answering these types of questions. I know a lot of people are visual learners, so maybe having steps written out will help you remember how to solve these. So if you look at step 1, identify the ionic charges of each element in the reactants in order to correctly write the products. Okay, so we need to look at each element in our reactants, figure out what the charge, what type of ion they form, and that will help us know if we're writing our products correctly. So I'm going to copy our first reactant here. I'll go up to the periodic table, and we'll figure out what the charges are. Okay, so the first element we have is sodium. Here's sodium on the periodic table. I'll make that a little thicker. Here's sodium on the periodic table. Sodium, since it's in this column forms +1 cations. So that means the charge of sodium is +1. Actually, I'll write that in a different color. So the charge of sodium is +1. Now, the anion in this compound is carbonate, which is a polyatomic ion. So if you have your polyatomic ions memorized, you should know the charge of carbonate. But if you don't, you can use the charge of sodium to help you figure out what the charge of carbonate is supposed to be. So we know that the charge of sodium is +1. And how many sodiums do we have? We have 2 sodiums. So if we have 2 +1s, that gives us an overall net charge of +2. So if we want this whole thing to be 0, what does that mean the charge of carbonate has to be? Well, what can we add to +2 to make it 0? -2. +2 and -2 is 0. That means the charge of the ion carbonate is -2. Okay, so we have +1 and -2. So we'll go back down to our reaction and we'll write that in. So we figured out that sodium is +1 and carbonate is -2. Okay, now let's look at our second reactant. I'll copy it. I'll go up here to the periodic table and paste. Okay, so we have silver and we have nitrate. So again, just like in the other example, this one's a little bit more difficult because silver right here is a transition metal, so it could have different charges for the ion that it forms. And nitrate's a polyatomic ion. So if you don't have your polyatomic ions memorized, then this question is going to be really difficult because you don't really have anything to help you figure out what the charges are supposed to be. But if you do have your polyatomic ions memorized, you'll know that the charge of nitrate is -1. So if the charge of nitrate is -1 and this whole thing has to equal 0, that means the charge of silver has to be +1. +1 and -1 equals 0. So we figured out the charge charges of our second reactant. So we'll go back down here to our reaction and we'll write that in. So silver is a positive 1 and nitrate is a negative 1. Okay, now let's write what our products are supposed to be. So we know that our cations are supposed to stay in the same spot. So our cations in this reaction are sodium and silver. So we're going to have sodium and silver. Now, one big mistake that students tend to make is that they see a 2 right here, and so therefore they're going to put a 2 right here. And you do not want to do that. Just because there are a certain amount of an element on the reactant side does not mean that the subscript is going to be the same on the right-hand side. Remember, we add subscripts to deal with differences in charges of the ions. So we can't write any subscripts until we figure out, well, what's the anion that each of these cations is going to be paired with. So don't make that mistake. Don't automatically, this 2 right here does not travel with the sodium, okay? The sodium goes by itself. The 2, the subscript 2, stays on that side. Okay, so if we look at our 2 anions are carbonate and nitrate. So carbonate on the reactant side was paired with sodium, so that means on the product side, we want it to be paired with silver. Oh, sorry, I forgot to write our charges for sodium, we said was +1, and silver is also +1. Okay, so make sure you write your charges on the products. Okay, so we want carbonate to be paired with silver. So carbonate is CO3, and we determined that it has a charge of -2. So is this product okay written like this? No, it's not, because there's not an overall 0 charge. We have -2 and +1. So what can we do here to make the silver have an overall charge of +2 to cancel out with the -2 of carbonate? We want another silver. But remember, when we want to add amounts of an element for the sake of ionic charges, we add subscripts, not coefficients. So I'm going to want to put a subscript 2 right here. And what that does is for silver, we have 2 +1s, which gives us a total of +2. And the charge of carbonate is -2. So -2 and +2 cancel out and equals 0. And so this would be the correct formula. So do not put a coefficient of a 2 in front of don't do this, basically. Okay? That is something different than putting a subscript 2 right here. So we added a subscript for the sake of ionic charges. Okay. So now let's look at our other anion of nitrate. So nitrate was paired with silver. So on the product side over here, we're going to want it paired with sodium. So I'll write NO3 right here. And we already figured out the charge was -1. So is this product okay? -1, +1? Yep, those cancel out and equals 0. So that product, just how it's written, is perfect. Okay, so now we've done steps 1 and 2. We identified the ionic charges of each element in the reactants. So right here, that's what we did here, 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 and here. And we use those charges to help us be able to write our products correctly. Okay, so we don't really need these anymore. Okay, now we need to determine if each of the products is soluble or insoluble. So we do that by looking at the anions. So here's our first anion, nitrate. If we look for nitrate on this list, here it is right here. It's generally soluble, meaning it dissolves in water, so the state would be aqueous, and it doesn't have any exceptions. So that means that we can write aqueous. Okay, now let's look at our other anion, which is carbonate right here. Let's find carbonate on the list. Where is it? Right here. Carbonate is generally insoluble unless it's paired with NH4 or any alkali metals. Is silver an alkali metal? No, it's not. It's a transition metal. So that means that silver, this silver carbonate compound, is insoluble. And since it's insoluble, that means it forms a precipitate. So this is going to be solid. Okay, now we've completed step 3. We've determined which of our products is soluble and which is insoluble. Now the last step is to make sure this equation is balanced. And again, when we balance, we want to keep our polyatomic ions together. And that will make our life a lot easier. Okay, so let's see if this is balanced. So we have 2 sodiums, 1 carbonate, 1 silver, and 1 nitrate. And here we have 1 sodium, 1 carbonate, 2 silvers, and 1 nitrate. Okay, so this equation is not balanced. So I'm going to look at the sodiums first. So there's 2 on the left and only 1 on the right. So if I put a 2 here, that's going to give me 2 sodiums. But remember, this 2 applies to this whole compound, so it's also going to give me 2 nitrates. Okay, now if we look at silver, there are 2 on the left, but only 1, there are 2 on the right, but only 2 on the left. So if I put a 2 right here, that gives me 2, and it also affects the nitrates, so that's going to give me 2 nitrates, and now it looks like we're balanced. Okay, so after all of that said and done, this right here is the final answer. This is the precipitation reaction that is a result of these two, this reactant and this reactant. So that would be your final answer. Okay, let's try to do one more together. So the first step is to figure out what the charges are of the charges of the ions for each element in our reactants, so that will help us know if we're writing our products correctly. So I'm going to copy this first reactant, and I'm going to paste it up here. Okay, so that's iron, right here, is a transition metal. So we can't really tell what the charge of the ion it forms is based upon its location on the periodic table. And sulfate is a polyatomic ion. So again, this is a situation where if you don't have your polyatomic ions memorized, you're not going to be able to figure this part of the question out. So if you do have your polyatomic ions memorized, you'll know that the charge that the ion sulfate forms is -2. So if sulfate is -2, what does that mean iron has to be? That means iron has to be +2. So now +2 and -2 cancel out, and the whole thing has an overall charge of 0. So +2 and -2. So we'll go back to our reaction and we'll write that in. So we have said iron was +2 and sulfate was -2. Okay, now let's take a look at lead and nitrate. Let me paste this up here. Okay, again, because lead is a transition metal, we can't figure out the charge based upon its location on the periodic table, and nitrate is a polyatomic ion, so you're going to have its charge memorized. If you have its charge memorized, you'll know that the charge is -1. But there are 2 of them, so that means the overall charge is what? So if we have -1 and -1, that means it's an overall charge of -2. So that means that the charge of lead has to be +2 to cancel out with that -2 and give the whole thing an overall charge of 0. So the charge of lead is +2. Okay. So we said lead was +2 and nitrate was -1. Okay, now let's write our products. So we know that our cations stay in the same place. So we're going to have Fe and Pb. and we'll write their charges. So Fe is positive 2, and Pb is also positive 2. Okay, now we know the anions need to switch places. So our first anion is sulfate. In the reactant side, sulfate is with iron. So on the product side, we're going to want it with lead. So I'm going to write SO4 right here, and then we write the charge. So we figured out the charge of sulfate is negative 2. So is this product okay, written how it like this, negative 2 and positive 2? Yes, right, because positive 2 and negative 2 cancel out equals 0, so there's a net charge. There's no net charge, so that product's okay. Now let's look at iron. All right, so what do we want to put with iron? Well, in the reactants, if we look at nitrate, nitrate was with lead, so now we're going to want nitrate to go with iron. So we're just switching the places. So I'm going to write NO3. And for nitrate, we said the charge was negative 1. Okay, so is this product written okay? Positive 2 and negative 1. No, it's not okay because there is not a net charge of 0, right? Because we have positive 2 and negative 1. So what can we do to make the net charge equal 0? Well, we can have another nitrate. So if I put parentheses, and I put a 2 right here, what does that do for us? That's saying that there are 2 negative 1s. So negative 1 and negative 1, that equals negative 2, and that cancels out with the positive 2 of iron. So now this is an okay formula. I'll erase that. Okay, so now our products are written correctly. Now we need to figure out, do either one of them form precipitates? So let's look at our anions. The first anion we can look at is nitrate. Nitrate is right here. And according to the table, it's generally soluble, and it has no exceptions. So that means that in this reaction, this product with the nitrate is soluble, meaning it's aqueous. All right, now let's look at our other anion, sulfate. Sulfate on the list is right here, so it's generally soluble unless it's paired with any of these. Do any of the exceptions apply? Yes, right? Because the cation it's paired with is lead, and lead is one of the exceptions. So that means that the sulfate is no longer soluble, but instead it's insoluble, meaning that it forms a precipitate. So the phase would be S for solid. Okay, so that's step 3. That is identifying each of our compounds as soluble or insoluble. Now the last step is to balance, keeping our polyatomic ions together. SO4, Pb, NO3, Fe, SO4, Pb, NO3. And if we look at how many we have on both sides, we'll see that there's 1 iron, 1 sulfate, 1 lead, and 1 nitrate. And on the other side, there are 2 nitrates. And on the other side, we have 1 iron, 1 sulfate, 1 lead, and 2 nitrates. Okay, so this equation is balanced. That means that this right here is our final answer. So this is saying that a precipitate occurs when these 2 reactants come together. Sorry, there's supposed to be an aqueous here. So when these 2 aqueous reactants come together, a precipitate is formed. Okay, so that's pretty much how you do precipitation reactions. Hopefully that helped you understand a little bit better, but if it didn't, if you still have questions, please feel free to either send me a message or leave a comment, and I will try to explain the concept a little bit better to you.